Look up at the night sky, past the familiar glow of the moon and the wandering lights of our sister planets. Every single one of those tiny, steady points of light is a sun, and around many of those distant suns, worlds are spinning in the eternal dark. For most of human history, we could only wonder if any of those worlds were like our own. But today, that wonder is turning into one of the most profound discoveries in all of science. We are finding them planets orbiting other stars, and among them, a special few that scientists believe could be havens for life. This isn't science fiction anymore, it's the thrilling frontier of modern astronomy. We are living in the era where we are beginning to answer one of humanity's oldest and most profound questions. Are we alone? The search has moved from speculation to a targeted, data-driven hunt, and the early results are more incredible than we ever dared to dream. Today, we are embarking on a cosmic voyage to explore 25 of the most promising candidates, alien worlds that have captured the attention of astronomers and ignited the imagination of everyone who gazes at the stars. These aren't just random names in a catalogue. They are entire worlds with their own unique characteristics, each telling a story written in the language of gravity, light, and chemistry. We will dive into what truly makes a planet potentially habitable, moving beyond simple guesses to the specific, exciting evidence that places these worlds at the top of the list. It starts with the Goldilocks zone, that magical, narrow band of space around a star where temperatures are just right, not too hot and not too cold for liquid water to potentially exist on a planet's surface. But that's just the beginning of the story. We'll explore the fascinating clues that suggest some of these worlds might have vast, deep oceans sloshing beneath icy crusts, or thick, protective atmospheres that could nurture the fragile chemistry of life. This journey is about more than just a list of planets. It's about understanding our place in the cosmos. Every one of these distant points of light represents a possibility, a potential sister to our own pale blue dot. They are our cosmic neighbors, and the growing excitement in the scientific community is palpable because finding them changes everything. It redefines what it means to be a planet, what it means to be habitable, and ultimately, what it means to be alive in a seemingly infinite universe. So get ready to meet these extraordinary worlds, to understand why they are so special, and to feel the same sense of awe and curiosity that drives the scientists who are uncovering their secrets. The discovery of a true second Earth is no longer a matter of if, but when, and the candidates we are about to explore bring us closer than ever to that monumental day. Our journey begins not in some distant, unreachable corner of the galaxy, but practically on our cosmic doorstep, just 4.2 light-years away, a distance that is almost unimaginably vast yet stunningly close in the grand scheme of our Milky Way, orbits a world that has rewritten our understanding of our stellar neighborhood. This is Proxima Centauri b, a rocky planet circling the star nearest to our own sun, Proxima Centauri. The very existence of this world is profound. It tells us that planets, even potentially Earth-like ones, are not rare anomalies but could be common features throughout the cosmos. Proxima Centauri b resides squarely within what astronomers call the habitable zone of its star. This means it receives a similar amount of stellar energy from its sun as the Earth does from ours, creating the tantalizing possibility that temperatures could be just right for liquid water to pool and flow on its surface. Think about that for a moment. The most fundamental ingredient for life as we know it could exist on a world orbiting the very next star over. This isn't a far-fetched concept from a story. It is a scientific fact based on years of painstaking observation and data collection. The planet itself is a super-Earth, a bit more massive than our own world, which suggests it likely has a solid surface you could stand on, with mountains, valleys, and perhaps even vast oceans. But the story of Proxima Centauri b is also a tale of cosmic extremes, a reminder that a place in the habitable zone doesn't automatically mean a tranquil, Earth-like paradise. Its host star, Proxima Centauri, is a red dwarf, a much smaller, cooler, and far more tempestuous star than our stable Sun. Red dwarfs are notorious for their violent outbursts, unleashing massive stellar flares that can bombard any nearby planets with intense bursts of X-rays and ultraviolet radiation. For a planet like Proxima Centauri b, which orbits very close to its dim star to stay warm, these flares pose a monumental challenge. They have the potential to scorch the surface and over billions of years strip away a planet's atmosphere, leaving it a barren, airless rock exposed to the harshness of space. So, the central, haunting question about this nearby world is not just whether it has water, but whether it has managed to hold onto a protective blanket of air. An atmosphere could shield the surface from the worst of the stellar radiation and help maintain a climate where liquid water, and perhaps even life, could persist. Scientists are actively investigating this very puzzle, using our most powerful telescopes to search for the chemical signatures of an atmosphere. The discovery of Proxima Centauri b transformed it from an abstract possibility into a tangible, nearby target for future exploration. It stands as a symbol of both immense promise and sobering reality in the search for habitable worlds, a constant reminder that the universe is full of complex and wondrous environments waiting to be understood. And this proximity to its star introduces one of the most significant hurdles for potential life on Proxima Centauri b, the strong likelihood that it is tidally locked. Imagine a world where the concept of a day and night cycle simply doesn't exist. One hemisphere is perpetually bathed in the dim, reddish glow of its sun, a landscape of constant, if feeble, daylight. The other side is plunged into an endless, deep freeze of night, a cold so profound it's difficult to comprehend. This isn't just a minor environmental quirk. It's a planetary condition that creates two utterly alien and potentially hostile extremes. The star-facing side could be blisteringly hot, while the dark side might be cold enough to freeze the very air itself, creating a world with a scorching face and a frozen skull. For a long time, scientists believed this tidal locking would be a death sentence for habitability, rendering the planet a stark world of two halves with no comfortable middle ground. But nature is often more ingenious than our initial assumptions. The key to bridging this dramatic divide could lie in a robust atmosphere. If Proxima Centauri b has managed to hold onto a substantial blanket of air, that atmosphere could act as a giant, planet-wide heating and cooling system. Winds of immense power could constantly rage, flowing from the hot day side to the cold night side, circulating heat and moderating the temperature extremes. This atmospheric engine might just create a narrow, temperate band along the boundary between perpetual day and eternal night, a twilight region known as the Terminator line. In this fragile ribbon of a habitat, conditions could be surprisingly stable, with temperatures that could allow for liquid water to exist on the surface. It's a fascinating thought that life, if it exists there, might not be spread across global continents, but huddled in a delicate ring of habitability, clinging to the edge of light and dark. This complex interplay of stellar violence, tidal forces, and potential atmospheric rescue makes Proxima b a world of profound contradictions and a primary target for the next generation of telescopes, which will seek to answer the critical question of whether this nearby world is a hostile wasteland or a hidden oasis. But the discovery of a single nearby world was only the beginning of a much larger revelation. If Proxima Centauri b hinted that planets might be common, then the TRAPPIST-1 system declared it with a cosmic shout. Located just under 40 light-years away, this system is home to not one or two, but 7 rocky planets, an entire family of Earth-sized worlds orbiting a single, faint star. It's a compact solar system that utterly redefines our idea of what's possible. The star at its heart, TRAPPIST-1, is an ultra-cool dwarf, so small and dim that it's only slightly larger than the planet Jupiter, glowing with a faint, reddish light. Because the star is so cool, its habitable zone is incredibly close in. all 7 of its known planets orbit closer to their star than Mercury does to our Sun. This proximity creates an astonishing cosmic ballet. From the surface of one of these worlds, the other planets would appear as magnificent, large globes in the sky, sometimes even showing discernible disks like moons. A year on the innermost world passes in just a day and a half, while a year on the outermost takes only about 20 Earth days. This entire, intricate planetary system would fit comfortably within the orbit of Mercury in our own solar system, a testament to a completely different architectural plan for building worlds. Of this remarkable family, one world stands out as a prime candidate for habitability, TRAPPIST 1e. This planet sits squarely in what astronomers call the conservative habitable zone, a more rigorous definition that narrows down the region where an Earth-like planet could maintain liquid water over geological timescales. The data we have is incredibly promising. TRAPPIST 1e is almost exactly the same size as Earth and has a very similar density. This similarity in density is a crucial clue. It strongly suggests that TRAPPIST 1e is a rocky world composed of iron, rock, and silicates, just like our own planet. It likely has a solid surface with familiar geological features, mountains, craters, and perhaps most excitingly, basins that could hold liquid water. Scientific models that simulate the potential climates of this distant world indicate that it could very well have surface temperatures remarkably similar to Earth's average. Imagine a world where the thermometer reads a comfortable, temperate range, a place where water wouldn't instantly boil away nor be permanently frozen solid. This combination of Earth-like size, Earth-like composition, and potentially Earth-like temperatures makes TRAPPIST 1e one of the most Earth-analogous planets we have ever discovered beyond our solar system. The potential doesn't stop at a solid surface and comfortable temperatures. The true allure of TRAPPIST 1e lies in the possibility of it being a water world. Some of the most sophisticated atmospheric modeling suggests that if this planet formed with a significant amount of water, a common ingredient in the planetary formation process, it could easily have held onto it. The result might be a global, deep ocean, a single uninterrupted body of water encircling the entire globe. Unlike Earth with its distinct continents and ocean basins, TRAPPIST 1e could be a planet of unbroken blue, a world with no dry land in sight. Its surface might be a global ocean, potentially hundreds of kilometers deep, with water pressure at the bottom so immense that it forms exotic types of ice, even in relatively warm conditions. This raises fascinating questions about the potential for life. On Earth, life thrives in the deepest, darkest ocean trenches around hydrothermal vents that spew mineral-rich water and provide chemical energy. A world like TRAPPIST 1e could be dotted with such vents across its entire seabed, creating a vast subsurface network of potential habitats completely isolated from the conditions on the surface. Of course, the habitability of any planet in the TRAPPIST 1 system hinges on the behavior of its star and the presence of an atmosphere. Like Proxima Centauri, TRAPPIST 1 is a red dwarf, and it too is prone to flares. However, there's a nuance here. Being an ultra-cool dwarf, TRAPPIST 1 is generally quieter and less violent than some of its larger red dwarf cousins, which could have given its planets a better chance to develop and retain atmospheres. The critical, ongoing scientific work involves using telescopes like the James Webb Space Telescope to peer at TRAPPIST 1e as it passes in front of its star. By analyzing the starlight that filters through the planet's limb, astronomers can search for the chemical fingerprints of gases like carbon dioxide, ozone, or methane. Detecting a thick atmosphere would be a monumental step forward, suggesting the planet is not only protected from stellar radiation but also has an active climate system. The discovery of the TRAPPIST 1 system was a watershed moment, demonstrating that small, rocky planets can form in large numbers and crowd around their star. And within that crowd, TRAPPIST 1e shines as a jewel, a world that checks nearly every box we have for a potentially habitable environment, inviting us to wonder what secrets might lie beneath its possible skies or within its hypothetical global ocean. While Proxima b and Trappist 1e orbit faint red dwarfs, our search for habitable worlds leads us to a different and equally compelling story with a landmark discovery. The Kepler Space Telescope, a mission that fundamentally changed our view of the galaxy, revealed a world that captured the public imagination like no other before it, Kepler 186f. This was the first rocky planet we ever found that was almost exactly the size of Earth, and it was sitting perfectly within the habitable zone of its own sun. The discovery in 2014 was a pivotal moment, a proof of concept that planets like ours were not just theoretical, but real and detectable across the vast interstellar distances. Kepler 186f is located about 500 light-years away in the constellation Cygnus, and its significance cannot be overstated. Before its discovery, we had found larger planets, often called super-Earths, in habitable zones, but Kepler 186f was different. With a radius just 10% larger than our own planets, it crossed a critical threshold. This small size makes it extremely difficult for the world to hold onto a thick, crushing atmosphere of hydrogen and helium like a gas giant. Instead, everything points toward a rocky composition, a world with a solid surface of rock and metal, much like Earth, Mars, or Venus. The star it orbits, Kepler 186, is still a red dwarf, but it provides a fascinating contrast to the stars we've discussed. This system offers a glimpse into a different kind of environment. While the star is smaller and cooler than our Sun, Kepler 186f orbits at a much more comfortable distance than planets like Proxima b. Its year is about 130 Earth days, meaning it's significantly farther out from its star's violent temper. This greater distance could be a major advantage for habitability. It potentially places the planet outside the zone of the most severe stellar flares and coronal mass ejections that can batter worlds closer in, giving it a far better chance of holding onto a protective atmosphere over billions of years. The amount of stellar energy it receives from its sun is about 1/3 of what Earth gets from the sun. At first, that might sound chilling, but here's where the possibility gets truly interesting. If Kepler 186f has a thicker atmosphere than Earth's, with a significant amount of greenhouse gases like carbon dioxide, that atmospheric blanket could trap enough heat to create very temperate, stable surface conditions. We have a perfect example of this in our own solar system. Mars is a frozen desert today, but scientists believe it was once warmer and had liquid water thanks to a thicker atmosphere in its past. Kepler 186f could be a planet that successfully maintained that delicate balancing act. This world also presents a captivating mystery regarding its rotation. Unlike the tidally locked planets orbiting ultra-cool dwarfs, a planet like Kepler 186f, farther out from a comma red dwarf, might very well have a day-night cycle similar to Earth's. It could be spinning on its axis, creating familiar cycles of daylight and darkness. The presence of such a cycle is another positive mark for potential habitability, as it would prevent one side of the planet from becoming lethally hot while the other freezes solid. It would allow for a more even distribution of stellar energy, fostering global climate patterns and weather systems that could be far more Earth-like. This combination of factors, an Earth-like size, a stable orbit within the habitable zone, a potentially milder stellar environment, and the possibility of a rotating world makes Kepler 186f a quintessential candidate for a life-friendly planet. It stands as a historic beacon, a world that told us Earth-sized planets in the Goldilocks zone were not just possible but waiting to be found. It expanded the playing field and gave us a new template for what to look for, proving that our own pale blue dot has cousins scattered throughout the galaxy, each with its own unique story of formation and evolution. Moving from the smaller red dwarf stars to a more familiar stellar type, we arrive at a planet that truly deserves its nickname. Welcome to Kepler 452b, a world so reminiscent of our own that scientists often refer to it as Earth's cousin. This isn't just poetic license, the similarities are striking and profound. Discovered by the Kepler telescope in 2015, Kepler 452b orbits a star named Kepler 452, which is a G-type main sequence star, the exact same classification as our own Sun. This star is only about 20% brighter and 4% more massive than the Sun, and it's roughly the same temperature. This marks a significant departure from the red dwarf systems we've explored. Here, we have a planet orbiting a star that is, for all intents and purposes, a near twin of our Sun, and one that is about 6 billion years old, making it 1.5 billion years older than our own star. This single fact opens up a monumental possibility. If Earth-like planets form around Sun-like stars, and if life is a natural outcome on such worlds given enough time, then Kepler 452b has had a significantly longer head start. Imagine a world that has had an extra 1.5 billion years for its geology, chemistry, and perhaps even biology to evolve and mature. The planet's orbital characteristics only deepen the sense of familiarity. Kepler 452b resides firmly within its star's habitable zone, but its position is what makes it so compelling. Its year lasts 385 Earth days, which is remarkably close to our own 365-day orbit. Even more critically, the amount of energy it receives from its host star is calculated to be just 10% more than what the Earth receives from the Sun. This tiny difference is well within the range of what a planetary climate system could easily regulate, especially if it has an Earth-like atmosphere with stabilizing feedback loops. This is a far cry from the faint, reddish-glow bathing planets like those in the TRAPPIST-1 system. This is a world that would experience sunlight very much like our own. From the surface, the Sun in the sky would appear almost indistinguishable from our own, casting similar shadows and providing a similar quality of light to drive photosynthesis, should any plant-like organisms have evolved there. The combination of a Sun-like star and an Earth-like orbital distance makes this one of the most convincing analogues to our own planetary home we have ever found. With a diameter about 60% larger than Earth's, Kepler 452b falls into the category of a super-Earth. This size has important implications. A planet of this scale has a much better chance of being a geologically active world. It would likely have a massive iron core, generating a strong magnetic field that could act as a vital shield, deflecting the stellar wind from its Sun-like star and protecting any potential atmosphere from being slowly eroded away over billions of years. Furthermore, the greater mass and internal heat would probably drive vigorous plate tectonics. On Earth, plate tectonics is a critical planetary thermostat. It recycles carbon dioxide between the atmosphere and the mantle, preventing a runaway greenhouse effect or a global freeze. This long-term climate regulation is considered by many scientists to be a key ingredient for sustaining habitability over geological timescales. The older age of the system suggests that if Kepler 452b is indeed Earth-like, it has had ample time for such stabilizing systems to develop and maintain a stable environment. Of course, the major unknown that defines the current scientific mystery surrounding this world is its composition. We know its size, but not its mass, which means we cannot yet calculate its density to confirm if it is truly a rocky world like Earth or a mini Neptune with a small rocky core enveloped by a thick, gaseous atmosphere. The sheer age of the system offers two fascinating, albeit speculative, scenarios. In one, the planet is a massive, water-rich world, having had billions of years more than Earth for water to accumulate and for its oceans to deepen. It could be a vast global ocean with no land masses in sight, a planet where life, if it exists, is exclusively aquatic. The other, even more captivating possibility is what scientists call the runaway greenhouse scenario. Given that the star has grown brighter as it has aged, just as our Sun will, the 10% extra insolation the planet receives today might have been significantly less in the distant past. It's possible that for most of its history, Kepler 452b was a perfect twin of Earth. But as its star slowly brightened, the planet may have crossed a critical threshold, causing its oceans to evaporate and a thick, water vapor-dominated atmosphere to trigger an irreversible greenhouse effect, turning it into a scorching hellscape like Venus. This possibility is a sobering reminder of Earth's own distant future, as our Sun will also increase in luminosity over billions of years. Kepler 452b, therefore, is not just a snapshot of a potential sibling world. It is also a potential window into our own planet's far future, a cosmic laboratory showing us one possible path a temperate, Earth-like world might take over immense stretches of time. But the search for habitable worlds is not just about finding Earth's twin. It's also about understanding the incredible diversity of environments where life could potentially take hold. This brings us to a particularly intriguing and massive world, LHS 1140b, a super-Earth that presents a fascinating puzzle for astronomers. Located 49 light-years away in the constellation Cetus, this planet is a heavyweight with a mass about 6.5 times that of Earth and a diameter roughly 1.4 times larger. That size and mass tell us something crucial about its density, and the numbers point to a composition that is far denser than our own world. This isn't a puffy gas mini-Neptune. It's a substantial rocky planet, likely with a huge iron core and a strong gravitational pull. What makes LHS 1140b so compelling, however, is its location, sitting firmly within the habitable zone of its calm red dwarf star. And when we say calm, that's a key distinction. Unlike the tempestuous Proxima Centauri, the star LHS 1140 is remarkably quiet for a red dwarf, exhibiting very low levels of flare activity. This stellar tranquility is a gift for any potential atmosphere, giving it a much better chance of surviving intact over billions of years without being stripped away by violent stellar winds. It's a stable platform for the development of a complex planetary environment. The high density of this world has led scientists to propose two captivating and very different scenarios for what it might be like. The first possibility is that LHS 1140b is a vast water world. Imagine a planet with a rocky core, but enveloped by a layer of water so deep it constitutes a significant fraction of the entire planet's mass. This wouldn't be an ocean like our Pacific. It would be a global feature hundreds of kilometers deep, with pressures at the bottom so immense that the water forms exotic, hot forms of ice. On such a world, there would be no continents, no beaches, just an unbroken expanse of water from pole to pole, potentially capped by a thick, steamy atmosphere. The second, and perhaps more likely, scenario is that it is a snowball planet. Given its substantial mass and the fact that it receives less stellar energy than Earth, its surface could be entirely encased in a global ice shell, much like Jupiter's moon Europa or Saturn's moon Enceladus, but on a planetary scale. For a long time, a global ice cover was thought to be a death knell for habitability, sealing a world off from the energy of its star, but we now know that's not necessarily the case. This is where the concept of a life-supporting ice shell comes into play, and it's a concept that turns a frozen world into a potential oasis. Even under miles of ice, a planet can remain geologically active. The immense gravitational tug from its star, combined with the heat from radioactive elements decaying in its core, could provide more than enough energy to keep a vast subsurface ocean in a liquid state. LHS 1140b, with its large iron core, is a prime candidate for such internal heating. This means that beneath a dark, frozen, and cratered surface, there could be a warm, saltwater ocean, completely global in extent, hidden from the cold of space above. We see this phenomenon at work in our own solar system on Europa, where a subsurface ocean may contain more than twice the water of all Earth's oceans combined. On LHS 1140b, this hidden sea could be a truly enormous environment, a dark, watery abyss that has been stable for billions of years. And just as scientists speculate about hydrothermal vents on the ocean floors of Europa or the seafloor of Enceladus, this super-Earth's ocean floor could be dotted with similar vent systems. These geysers on the seafloor would spew mineral-rich, warm water into the ocean, providing not only heat but also the chemical building blocks and energy gradients that could potentially fuel an entire ecosystem of life, completely independent of sunlight. The surface of such a world would be a frozen, silent desert, but below, in the perpetual darkness, a rich and complex biosphere could be thriving, utterly unaware of the starry sky above. The recent observations hinting at a nitrogen-rich atmosphere for LHS 1140b only add to the intrigue, as such an atmosphere could help moderate surface temperatures and contribute to the complex chemistry needed for life. This super-Earth stands as a powerful reminder that habitability is not a one-size-fits-all concept. A world that appears frozen and dead on the outside might be hiding the most vibrant of secrets deep within. Now let's turn our attention to a system that feels almost like a next-door neighbor in galactic terms. A mere 12.5 light-years away, one of the smallest and faintest stars in our celestial neighborhood hosts a world that ranks among the most Earth-like we have ever discovered. Welcome to Teegarden Star B. Its host star is a dim red dwarf, so faint it wasn't even discovered until 2003 despite its proximity. This ancient star is billions of years old, offering any potential life an immense span of time to emerge and evolve. What makes this particular planet so exceptional is its Earth Similarity Index, a score of 0.95. This metric, developed by astronomers, compares a world's key properties to our own, with a perfect match being 1.0. With a score that high, Teegarden Star B sits at the very top of the list, suggesting its surface temperature and the levels of stellar energy it receives are strikingly similar to the conditions we enjoy here on Earth. This isn't just a world in the habitable zone. It's a world whose fundamental environmental parameters appear to mirror our own more closely than almost any other known exoplanet. The planet's orbital position is a key part of this remarkable similarity. Teegarden Star B completes a full orbit around its dim sun in just 4.9 Earth days. While that sounds incredibly fast, the star it circles is so exceptionally cool and faint that the planet must huddle close to stay warm. This proximity places it squarely in the center of the star's habitable zone, receiving an amount of stellar radiation that is almost identical to what Earth receives from the Sun. Imagine standing on the surface of this world. The sun in the sky would be a deep, dark red orb, much larger in apparent size than our sun, but providing a gentle, twilight level of illumination. The temperature, however, could be remarkably comfortable. If this planet possesses an atmosphere with a composition similar to Earth's, with the right mix of nitrogen, oxygen, and some greenhouse gases, its average global temperature could theoretically be very close to our own, potentially allowing for liquid water to flow freely across its surface. This combination of factors creates a powerful picture of a world that, on paper, seems almost tailor-made for life as we know it. However, as with all red dwarf systems, there are significant challenges to consider. Teegarden Star is a very quiet and stable red dwarf, which is a major advantage as it subjects its planets to far less flare activity than stars like Proxima Centauri. This calm stellar behavior greatly increases the chances that Teegarden Star B could have retained a substantial atmosphere over its long history. The critical unknown and the focus of intense scientific interest is whether this world is tidally locked. Given its close orbit, it is highly probable that one hemisphere permanently faces the star in endless day, while the other is turned away in eternal night. Yet, as we've seen with other worlds, a thick atmosphere could work to distribute heat, potentially creating a habitable band along the terminator line. Alternatively, if the planet has a global ocean, the currents could transport warmth from the day side to the night side, preventing the entire dark side from freezing solid. The high Earth Similarity Index score powerfully suggests that, whatever its rotational state, the overall energy balance of the planet results in a climate that could be surprisingly Earth-like. The ancient age of the system adds another layer of profound possibility. This star and its planets have existed for 8 billion years or more, double the age of our own solar system. If life did emerge on Teegarden star B, it has had an almost unimaginable amount of time to develop, diversify, and become complex. The discovery of this nearby, highly Earth-like world transforms a faint, insignificant star into one of the most compelling targets for future study, a place that challenges our understanding of habitability and reminds us that an Earth-like environment might be flourishing just 12 light-years away. Just when we thought we had a handle on the challenges of red dwarf systems, a world emerges that seems to have won the stellar lottery. A short cosmic hop away at 11 light-years, Ross 128b presents a scenario that has scientists genuinely excited. What sets this Earth-sized planet apart isn't just its location in the habitable zone, but the remarkably calm nature of the star it calls home. While many red dwarfs are tempestuous and unpredictable, Ross 128 is what astronomers call an inactive flare star. It's a placid, stable beacon, offering its planets a consistent and gentle flow of energy without the violent, atmosphere-stripping tantrums that plague worlds like Proxima b. This stellar serenity cannot be overstated. For billions of years, this tranquility would have provided a stable environment, giving Ross 128b a far greater chance to develop and, crucially, retain a life-sustaining atmosphere. The planet itself is a fascinating subject. It orbits extremely close to its star, completing a full year in just under 10 Earth days. Yet, because the star is so cool, this tight orbit is precisely what places it within the habitable zone. The amount of stellar energy it receives is only about 38% more than what the Earth gets from the Sun. This is a critical detail. That extra energy is well within the range that a planetary atmosphere could manage. For instance, if Ross 128b has an atmosphere with a slightly higher reflectivity or cloud cover than Earth's, it could easily bounce that extra sunlight back into space, maintaining a comfortable surface temperature. Alternatively, a thinner atmosphere might still allow for liquid water, especially if the planet has a robust geological cycle to regulate carbon dioxide levels. This places it in a very different category from planets that receive double or triple the stellar radiation, where runaway greenhouse effects become a near certainty. The possibility of tidal locking is still present, given its close orbit, but the calm nature of its star completely changes the equation for what a locked world could be like. Without violent flares to scour the day side and tear away at the atmosphere, the planet's air could effectively circulate heat from the perpetual day hemisphere to the frozen night side. This could create a much wider and more stable temperate band than would be possible on a more violent star. Scientists are particularly eager to point next-generation telescopes at Ross 128b because its quiet star creates a pristine background. Trying to detect the faint signature of an atmosphere in the starlight filtering through a planet's air is incredibly difficult if the star itself is constantly flickering and flaring. With Ross 128's steady glow, the signal from the planet's atmosphere will be far clearer and easier to read, giving us our best chance yet to detect the gases surrounding a temperate, Earth-sized world around a red dwarf. The implications of finding an atmosphere on Ross 128b would be revolutionary. It would tell us that rocky planets can not only form in the habitable zones of the most common stars in the galaxy, but that they can also find stable, long-term homes there. This world stands as a testament to the idea that while the universe can be a violent place, there are also pockets of profound stability, quiet corners where the conditions for life could persist for eons. It shifts the search from simply finding planets in the right place to finding planets in the right place around the right kind of star, making Ross 128b not just another candidate, but a blueprint for a specific and perhaps common kind of habitable world. Now let's venture into a stellar arrangement that sounds like it's straight out of a science fiction epic. 22 light-years from Earth lies the GJ667 system, a celestial dance of not one, not two, but three stars gravitationally bound together. And within this complex triple star system, we find a world that defies simple categorization, GJ667cc. This super-Earth, with a mass at least 3.8 times that of our own planet, orbits the smallest star in the trio, a red dwarf designated GJ667c. Its orbit places it squarely in the star's habitable zone, and the calculations of the stellar energy it receives are strikingly familiar. It's nearly identical to the amount of energy that bathes our own Earth from the Sun. So on paper, we have a massive rocky world with an Earth-like energy budget, a combination that makes it an incredibly compelling candidate in the search for life. But the true uniqueness of this world isn't just its size or its position, it's the sky that would hang above it. Imagine a sunrise where the primary sun, a K-type star, glows with an orange hue in the distance. The other two stars in the system would appear as brilliantly bright stars in the daytime sky, far outshining Venus as seen from Earth, and they would go through a complex, mesmerizing dance of conjunction and opposition over periods of many years. For parts of its long year, the planet would experience periods of continuous daylight from multiple sources, a permanent twilight illuminated by 2 or even 3 suns. This creates a climate puzzle of incredible complexity. On Earth, our stable seasons and climate patterns are largely dictated by our singular, consistent relationship with one star. On GJ667cc, the gravitational tugs and varying light from 3 different stars would introduce fluctuations that could make long-term climate stability a monumental challenge. The planet's axis could wobble unpredictably over millennia, leading to dramatic shifts in temperature and weather patterns that are difficult to even model. However, this very complexity might also be the key to its potential habitability. The planet's substantial mass is a huge advantage here. A world this massive would have a tremendous gravitational pull, making it extremely difficult for its atmosphere to be stripped away by solar winds, even in a more chaotic stellar neighborhood. This strong gravity would also likely foster a powerful magnetic field, generated by a churning molten core, offering another layer of protection. Furthermore, that same mass suggests the planet could be a water world on a grand scale. Having more gravity to hold onto volatile compounds, it could have accumulated vast reservoirs of water during its formation. The surface could be a global, deep ocean, and the immense pressures at the bottom of such an ocean could create a stable environment insulated from the climatic chaos happening in the skies above. Life could potentially find a refuge in those dark, deep waters, thriving around hydrothermal vents on the ocean floor, completely isolated from the shifting patterns of light and shadow created by its 3 suns. GJ667cc stands as a powerful testament to the diversity of habitable environments, suggesting that even in the most complex and seemingly unstable stellar systems, nature may find a way to create conditions ripe for life. Shifting our gaze to a planetary system that feels like a more distant cousin to our own, we find Kepler 62f, a world that showcases the resilience of potential habitability. Located about 1,200 light-years away in the constellation Lyra, this planet is part of a remarkable family of at least 5 worlds orbiting a star noticeably cooler and smaller than our Sun. What makes Kepler 62f so compelling is its steadfast position. Its entire 267-day year is spent nestled securely within the heart of its star's habitable zone. Unlike some planets that may only graze the edges of this life-friendly region, this world is a permanent resident, enjoying stable stellar energy conditions for its entire orbit. Its size, about 40% larger than Earth, places it firmly in the super-Earth category, but the most exciting revelations come from sophisticated climate modeling. These simulations paint a picture of a world with a remarkable capacity for stability. The research indicates that Kepler-62f could potentially maintain liquid water on its surface across a surprisingly wide range of atmospheric conditions. This resilience is a key part of its story. For a planet to be truly habitable, it needs to be able to withstand changes over geological time. A world that can only support water with a very specific, fragile atmospheric composition might lose its habitability easily. Kepler-62f, however, appears to be far more robust. Scientific studies have explored various scenarios, from atmospheres thicker than Earth's to those significantly thinner, and even models where its axial tilt is much more pronounced, leading to extreme seasons. In many of these simulations, the planet still manages to maintain temperatures above freezing across large portions of its surface. This suggests a built-in buffer, a climate system that could be forgiving and stable. Imagine a world where, even if the atmospheric pressure dropped or the concentration of greenhouse gases fluctuated, the global average temperature would remain in a range that allows for vast liquid oceans to persist. This kind of environmental tenacity is a gold standard for astrobiologists, as it implies that habitable conditions on this world could be long-lasting and difficult to disrupt. The planet's larger size also hints at fascinating geological possibilities. A super-Earth like this would have a stronger gravitational pull, which could help it hold onto a thick atmosphere over billions of years, protecting it from stellar winds. Furthermore, that additional mass likely means a hotter, more active interior. This internal heat engine could drive vigorous plate tectonics, a process that acts as a global thermostat on Earth by recycling carbon between the mantle and the atmosphere. On Kepler-62f, this continuous renewal could help regulate carbon dioxide levels, preventing the planet from swinging into a runaway greenhouse effect or a global ice age. The presence of active geology might also mean a varied and dynamic landscape, with towering mountain ranges, deep rift valleys, and perhaps widespread volcanic activity, all contributing to a complex and ever-changing environment where the chemical building blocks of life are constantly being circulated and renewed. Given the cooler nature of its host star, one might wonder if the surface would be too cold. This is where the potential for a strong greenhouse effect comes into play. If Kepler-62f has an atmosphere rich in carbon dioxide, that gaseous blanket could very effectively trap the limited heat from its sun, raising global temperatures to comfortable Earth-like levels. In fact, some models suggest that with a carbon dioxide atmosphere just a few times thicker than Earth's, the planet could easily have surface temperatures well above freezing. This presents two captivating visions of this distant world. In one, it is a lush, water-rich planet, a global ocean dotted with archipelagos of active volcanoes, its skies thick with clouds and weather systems driven by the warmth of its greenhouse blanket. In another, it could be a world emerging from a global ice age, with a bright, icy surface reflecting sunlight, yet with a thick atmosphere that keeps the equatorial regions warm enough for open water. Kepler-62f stands as a testament to planetary versatility, a world whose very design seems to favor the persistence of liquid water, making it one of the most promising and intriguing candidates for a life-supporting environment far beyond our own solar system. Now, let's turn our attention to a discovery that truly captured the imagination of the entire planet hunting community. From the vast data trove of the Kepler mission, a world emerged that was initially missed by computer algorithms, only to be spotted years later by the keen eyes of citizen scientists. This is Kepler 1649c, a planet that many have since called the most Earth-like world ever found by Kepler in terms of its fundamental physical characteristics. Lying 300 light-years away, this rocky planet orbits a quiet red dwarf star, and its statistics are nothing short of stunning. It's just 6% larger than our own planet, almost a perfect twin in size, and it orbits squarely within its star's conservative habitable zone. The amount of stellar energy it soaks up from its sun is 75% of what Earth receives, a figure that falls squarely within a range that could easily support liquid water with the right atmospheric conditions. Think about a world with a similar surface gravity to our own, under a sky with a dim red sun, but with a climate that could potentially be as mild and temperate as many places here on Earth. This combination of an almost identical Earth size and a very Earth-like energy budget is what sets Kepler 1649c apart, making it a standout candidate in the catalogue of potentially habitable worlds. The story of its discovery adds a wonderful human element to the science. It was found during a review of data that automated routines had previously discarded as noise or false positives. This underscores a vital truth in the search for other Earths. Sometimes the most profound discoveries are hidden in plain sight, waiting for a curious mind to recognize their significance. The planet's orbital period is also remarkably suggestive. It completes a year in just 19.5 Earth days, and fascinatingly, its orbit appears to be in a stable, near-perfect orbital resonance with another, more distant planet in the system. This kind of gravitational harmony is a strong indicator of a stable planetary system, one that has likely persisted for billions of years without violent upheavals. Long-term stability is a crucial, often overlooked ingredient for life. It provides the extended, peaceful intervals necessary for the slow, delicate processes of chemical evolution to possibly give rise to biology. A stable orbit within the habitable zone for eons is a powerful argument in favor of this world's potential. Of course, the central question, as with all red dwarf planets, revolves around its atmosphere and its rotation. The planet is likely tidally locked, presenting the now familiar scenario of a permanent day side and a perpetual night side. However, the fact that it receives 3/4 of Earth's stellar energy is a major advantage. This places it in a much more comfortable position than a planet receiving a similar amount of energy from a sun-like star. A red dwarf's light is heavily weighted toward infrared radiation, which is more efficient at heating a planetary surface and its atmosphere. This means that the potential for maintaining liquid water is actually enhanced. If Kepler 1649c has an Earth-like atmosphere, climate models suggest its average surface temperature could be almost identical to Earth. Even a relatively thin atmosphere could suffice to circulate heat and prevent the night side from freezing solid. The possibility of a global ocean is particularly strong here. A world with this much water could use oceanic currents to effectively transport warmth around the globe, creating a much more uniform and habitable environment than a dry, rocky world could ever achieve. This world represents a kind of sweet spot in the search. It's not so close to its star that it's bombarded by lethal radiation, nor is it so far out that it requires a massive greenhouse effect to stay warm. It sits in a Goldilocks position within the Goldilocks zone itself. The quiet nature of its host star further bolsters its case, giving it the best possible chance to hold onto the atmospheric blanket it needs to thrive. When you combine its near-Earth size, its Earth-like stellar flux, its apparent orbital stability, and its calm stellar host, you have a recipe for what is, on paper, one of the most promising abodes for life we have ever identified. Kepler 1649c serves as a powerful reminder of why we look, because sometimes the data reveals a world that feels less like a distant point of light and more like a potential home, a mirror of our own world spinning in the darkness, waiting for us to learn its secrets. And now we come to a world that has fundamentally changed the conversation in exoplanet science. Meet K2-18b, a super-Earth located 124 light-years away in the constellation Leo. For years, we had inferred the possibility of water on distant worlds based on their orbital position, but K2-18b delivered something far more concrete and electrifying. Detailed spectroscopic observations, primarily from the Hubble Space Telescope, detected the unambiguous signature of water vapor in its atmosphere. This was a landmark moment, a first in the history of astronomy. We were no longer simply inferring the potential for water on a habitable zone world. We were directly measuring it, confirming its presence in the skies of another planet. This discovery transformed K2-18b from a statistical possibility into a tangible, alien environment where one of the most fundamental ingredients for life is actively present. The planet itself is a fascinating subject. It's classified as a super-Earth or even a mini-Neptune, with a mass about 8 times greater than our own world and a radius over twice as large. This substantial size places it in a curious category, sitting right on the boundary between a massive rocky planet and a small, gaseous world with a thick, deep atmosphere. It orbits a calm red dwarf star, completing a full circuit in just 33 days. This short year places it squarely within the star's habitable zone, where temperatures could allow for water to exist in its liquid state. The detection of water vapor in its thick atmosphere is the central clue that has everyone so excited, but it also presents a complex puzzle. The presence of water vapor doesn't automatically mean there are blue oceans and sandy beaches down below. The atmosphere of K2-18b appears to be predominantly hydrogen-rich, a telltale sign of a world that formed with a deep, primordial gaseous envelope, much like the ice giants Neptune or Uranus in our own solar system. This leads to the two compelling and very different visions scientists have for this world. In one scenario, K2-18b is a Hycean world, a theoretical class of planet with a massive, global liquid water ocean beneath a thick, hydrogen-rich atmosphere. Imagine a planet with no solid landmass at all, just a seemingly endless ocean that could be tens to hundreds of kilometers deep, all capped by a dense, hazy atmosphere. The conditions at the bottom of such an ocean would be extreme, with pressures soaring to thousands of times what we experience at sea level on Earth. Yet, even there, life could find a way. We know that on Earth, extremophile organisms thrive around deep-sea hydrothermal vents, living off chemical energy completely independent of sunlight. A Hycean world could offer a vast global habitat for such life forms, a dark, deep biosphere that spans the entire planet. The other, perhaps more likely, possibility is that K2-18b is a mini-Neptune. In this model, the planet has a relatively small rocky and metallic core, but that core is enveloped by an immensely thick and deep layer of not just gas, but high-pressure ices and supercritical fluid water. There would be no well-defined surface ocean to speak of. Instead, the atmosphere would gradually get thicker and hotter as you descend, eventually transitioning into a bizarre, hot, and slushy mantle of water in a state that is neither truly liquid nor solid. The water vapor detected in the atmosphere would merely be the upper, cooler layer of this vast and alien hydrological cycle. For habitability, this is a much more challenging environment. Any potential life would have to survive not on a surface, but suspended within the atmospheric layers, or somehow endure the incredible pressures and temperatures deep within the planet's fluid interior. What makes the ongoing study of this planet so revolutionary are the additional chemical clues we are beginning to gather. Follow-up observations have tentatively suggested the presence of dimethyl sulfide, or DMS, in its atmosphere. On Earth, DMS is a gas produced almost exclusively by biological processes, specifically by marine phytoplankton. While the detection is not yet confirmed and could potentially be explained by non-biological geological processes, the mere possibility has sent ripples of excitement through the scientific community. It represents a glimpse into the next frontier of exoplanet science, the search for biosignatures. K2-18b is not just a world with water. It is a world that is now being scrutinized for the chemical fingerprints of life itself. It stands as a powerful testament to how far we have come, from simply discovering planets to studying their atmospheres, and now to beginning the painstaking work of looking for signs that we are not alone in the universe. The concept of a Hycean world is truly one of the most fascinating and alien possibilities in modern astronomy, and K2-18b stands as its prime real-world candidate. Imagine a planet where the very idea of a continent is obsolete. From pole to pole, there would be no mountains breaking the surface, no vast deserts or sprawling forests, just an unbroken global ocean, potentially hundreds of kilometers deep. This wouldn't be an ocean like our Atlantic or Pacific. It would be a planetary feature, a single body of water so immense its volume could dwarf all of Earth's oceans combined. The sky above this endless sea would not be the familiar blue we know, but rather shrouded in a thick, hazy atmosphere dominated by hydrogen, with clouds of water vapor creating a permanent global overcast. The pressure at the surface of this ocean would be crushing, not unlike the conditions at the bottom of Earth's Mariana Trench, but spread across the entire planet. Yet within this extreme environment, a unique form of habitability could emerge. The hydrogen-rich atmosphere, while not breathable for us, would act as a powerful greenhouse blanket, effectively trapping the faint heat from its red dwarf sun and maintaining temperatures at the ocean's surface that could allow for liquid water to exist. This creates a stable, if bizarre, aquatic environment that could persist for billions of years, offering a vast, dark, and watery stage for the chemistry of life to begin. The potential for life within such a global ocean hinges on the presence of what scientists call the base of the food chain. On Earth, our oceans are teeming with life because sunlight penetrates the surface, allowing phytoplankton to perform photosynthesis and create organic matter. But on a Hycean world, the thick, hydrogen-rich atmosphere and deep global cloud cover might block most sunlight from ever reaching the ocean's surface, plunging the waters into perpetual twilight or even absolute darkness. This might seem like a deal-breaker, but nature has already shown us another way. At the very bottom of Earth's oceans, far beyond the reach of the sun's rays, entire ecosystems thrive around hydrothermal vents. These are geysers on the ocean floor that spew superheated, mineral-rich water into the cold depths. The organisms there, from giant tube worms to bizarre crabs and microbes, don't rely on sunlight at all. Instead, they use a process called chemosynthesis, deriving energy from the chemical reactions between the vent fluids and the seawater. A planet like K2-18b, with its substantial mass, would almost certainly have a hot, geologically active core. The seafloor of its global ocean would likely be dotted with countless such hydrothermal vent systems, creating oases of chemical energy in the abyssal dark. In this scenario, life wouldn't need the sun. It could flourish in the deep, sustained by the planet's own internal heat and the constant cycling of minerals from its rocky mantle into the boundless waters above. This leads us directly to the most tantalizing clue in the atmosphere of K2-18b, the tentative detection of a molecule known as dimethyl sulfide, or DMS. On our planet, dimethyl sulfide is a gas produced almost exclusively by biological activity. Vast blooms of marine phytoplankton in Earth's surface oceans release DMS as a metabolic byproduct, and it eventually wafts into the atmosphere, where it can even play a role in cloud formation. Finding this specific molecule in the air of another world is therefore enormously significant, as it is considered a potential biosignature, a chemical signpost that could point toward the presence of life. It is absolutely crucial to temper excitement with scientific caution, as the detection is not yet confirmed and there is a possibility, however slim, that non-biological geological processes could produce the gas. But the possibility that this signal is real opens up a breathtaking narrative. It suggests that within the dark, global ocean of K218b, some form of life, perhaps vast colonies of microbes or even more complex organisms, could be thriving in such abundance that their collective metabolism is releasing gases that become detectable across 124 light-years of interstellar space. The idea that we might be smelling the breath of a distant biosphere is a profound one, pushing the search for life beyond our solar system into an entirely new and revolutionary phase. While K218b revealed the presence of water vapor in the atmosphere of a distant world, another landmark discovery was being made closer to home, this time by a new generation of planet hunters. Enter TOI 700d, a world that serves as a brilliant validation of NASA, a transiting exoplanet survey satellite, or TESS, mission. Launched to scan the entire sky for planets crossing in front of nearby bright stars, TESS delivered a spectacular find: an Earth-sized planet orbiting securely within the habitable zone of a quiet and stable star. This isn't a massive super-Earth or a mysterious mini-Neptune. TOI 700d is a world with a radius just over 100% that of Earth's, making it one of the very few truly Earth-sized planets we've found residing in that life-friendly orbital sweet spot. Its location is prime real estate in the cosmic sense, receiving about 86% of the stellar energy that Earth gets from the Sun. That small difference is easily within the range that a planetary atmosphere could compensate for, potentially creating surface temperatures that are remarkably similar to our own. What truly sets the TOI 700 system apart, however, is the serene nature of its host star. The star is an M-dwarf like many others we've encountered, but it belongs to a much calmer and more mature class. Critical observations have shown that TOI 700 displays no signs of dangerous flaring activity. This stellar tranquility is a game-changer. For a planet like TOI 700d, which orbits relatively close to its star with a year of just 37 days, a quiet sun means its potential atmosphere isn't being constantly bombarded and stripped away by violent X-ray and ultraviolet radiation. This gives the planet a fighting chance, a stable, billion-year-long opportunity to develop and retain the very air and climate that could make it habitable. It's the difference between living in a peaceful neighborhood and one that's constantly being hit by natural disasters. One environment fosters stability and growth, while the other leads to constant disruption and ruin. Scientists haven't just stopped at identifying its promising position. They have run sophisticated climate models to see how this world might actually behave, and the results are incredibly encouraging. These models have explored a wide range of possible atmospheric compositions, from a thick carbon dioxide, heavy atmosphere similar to a young Mars or Venus, to a thinner, nitrogen-rich atmosphere much like modern Earth. In many of these simulated scenarios, the planet consistently maintained conditions suitable for surface liquid water. One particularly compelling simulation suggested that if TOI 700d has an Earth-like atmosphere with a significant amount of cloud cover, those clouds would efficiently reflect just enough sunlight to keep the global climate temperate, preventing any runaway greenhouse effect. Another model, which assumed a thicker carbon dioxide atmosphere, showed that the greenhouse warming would be sufficient to prevent the planet from freezing over, creating a world with expansive open oceans. This climatic resilience is a powerful indicator of its potential. A planet that can support liquid water across a variety of atmospheric conditions is one that is robust. A world where habitable conditions are not a fragile, fleeting state, but a durable and long-lasting feature. The presence of other planets in this system adds another layer of intrigue and confidence to the discovery. TOI 700d is not alone. It shares its star with at least 2 other known worlds. This means we are not looking at a solitary, unusual planet, but part of a full-fledged planetary system. The discovery of multiple planets allows astronomers to better understand the formation history and dynamical stability of the entire system, and a stable system is far more likely to provide the long-term peace necessary for life to emerge and evolve. With its Earth-like size, its secure position in the habitable zone, its calm star, and its climate model resilience, TOI 700d ticks almost every box we have for a potentially habitable world. It stands as a testament to the power of modern astronomy, a world discovered by a new telescope that has quickly become one of the most promising places to look for the signs of a second Earth. While many of the worlds we've explored bask in the warmth of their stars, some of the most enduring habitats might be found in the cold, relying not on sunlight, but on the planet's own internal fortitude to create a sanctuary for life. This brings us to GJ 357d, a super-Earth discovered in 2019 that perfectly illustrates this principle of hidden warmth. Located a mere 31 light-years away, this planet is a substantial world with a mass at least 6 times that of Earth, orbiting a quiet red dwarf star. On the surface, its prospects might seem dim. The amount of stellar energy it receives from its sun is only slightly more than what Mars gets from our sun. If you were to place a rocky ball with a thin atmosphere at that distance, it would be a frozen desert, just like Mars is today. But GJ 357d is no ordinary rocky ball. Its significant mass is the key to unlocking a completely different and far more promising reality. A planet this massive has the gravitational strength to hold onto a very thick, dense atmosphere, and that changes everything. The true potential of this world lies in the power of that hypothetical atmosphere to act as an insulating blanket. Think of it like this: Mars is a cold world largely because its atmosphere is so thin, about 1% of Earth's, that it cannot trap any meaningful amount of heat. But if you were to wrap Mars in an atmosphere as thick as Venus's, which is 90 times denser than Earth's, its surface temperature would soar, easily melting ice and potentially creating stable bodies of liquid water. This is the precise climatic alchemy that could be at work on GJ 357d. If it formed with a substantial amount of volatile gases like carbon dioxide, water vapor, or even hydrogen, its strong gravity would have prevented those gases from escaping into space. Over billions of years, it could have built up a deep, planet-wide atmospheric shroud. This shroud would be incredibly effective at trapping the faint infrared radiation from its red dwarf sun, creating a powerful greenhouse effect that raises surface temperatures from a deep freeze to a comfortable, temperate range. In this scenario, the planet's surface could be dotted with lakes or even vast oceans of liquid water, all while receiving no more sunlight than the frigid, arid plains of Mars. It's a vivid demonstration that the habitable zone is not a fixed boundary, but a concept that expands and contracts based on a planet's atmospheric composition. A thick atmosphere can push the outer edge of the habitable zone much farther out, turning a seemingly icy world into a potential water world. This capacity for atmospheric-driven warmth opens up another captivating possibility for GJ 357d. That of a vast subsurface ocean sealed beneath a global ice shell. Even if the surface temperatures remain below freezing, the planet's large size points to a geologically active interior, heated by the relentless decay of radioactive elements in its core and the gravitational squeezing from its star. This internal heat has to go somewhere, and on a world with a solid surface, it could be enough to maintain a layer of liquid water trapped between the frozen crust above and the rocky mantle below. We see this phenomenon on a smaller scale with moons like Europa and Enceladus in our own solar system. On a super-Earth like GJ 357d, this subsurface ocean could be far more massive, a deep, dark sea that wraps the entire globe. Life in such an environment would be completely isolated from the surface, thriving in absolute darkness around hydrothermal vents on the ocean floor, drawing energy from the planet's own internal fires. The thick atmosphere, in this case, wouldn't be for greenhouse heating, but would instead serve as a protective barrier against cosmic radiation and impacts, helping to maintain the stability of the icy crust that protects the inner ocean. GJ357d stands as a powerful reminder that a planet's habitability is not written solely in the light it receives from its star, but also in the heat it generates from within, offering a second, hidden path for life to emerge in the cosmos. Moving on from the tightly packed systems of red dwarfs, we arrive at a world that offers a different kind of promise, one that echoes the familiar rhythms of our own planet. 42 light-years away in the constellation Pictor orbits HD 40307G, a super-Earth whose very orbit tells a story of potential stability. What sets this world apart is its journey around a K-type star, a star that is slightly smaller, cooler, and more orange than our Sun, but significantly larger and more stable than the red dwarfs we've encountered. This stellar context is crucial. K-type stars are often called Goldilocks stars by astronomers as they offer a compelling blend of longevity and calm. They burn for tens of billions of years, far longer than our Sun, providing an immense time span for life to develop, yet they are much less prone to the violent flaring that plagues their smaller red dwarf cousins. This creates a far more gentle and consistent environment for any planets orbiting within their habitable zones. The orbital characteristics of HD 40307G are particularly Earth-like and fascinating. This planet completes a full journey around its star in about 200 Earth days. This period is significant because it strongly suggests the planet is rotating on its axis with a regular day-night cycle. It is almost certainly not tidally locked. This means it experiences the familiar rise and set of its sun, and critically, it likely has seasons. Just like Earth, its axis is probably tilted, so as it travels along its 200-day year, different hemispheres would tilt toward and away from the star, creating cyclical changes in temperature and weather. Imagine a world with a spring, summer, autumn, and winter, a planet where the climate has a rhythmic, predictable pattern driven by its orbital dance. This kind of seasonal variation is a powerful engine for driving environmental diversity and could play a key role in the evolution of complex ecosystems. The amount of stellar energy it receives from its K-type host is remarkably similar to what Earth gets from the Sun, placing it firmly in the heart of the habitable zone where the conditions for liquid water are, from an energy perspective, ideal. As a super-Earth with a mass at least 7 times that of our own world, HD 40307G possesses several inherent advantages for habitability. That substantial mass translates to a stronger gravitational pull, which makes it exceptionally good at holding onto a thick, protective atmosphere over billions of years. An atmosphere is a planet's first line of defense against cosmic radiation and asteroid impacts, and it is the very medium that drives climate and weather. Furthermore, a planet of this size almost certainly has a robust and active internal heat engine. A large, molten iron core would generate a powerful global magnetic field, a vital shield that deflects the charged particles of the stellar wind and prevents the atmosphere from being slowly eroded away. This internal heat would also fuel vigorous geological activity, most likely in the form of plate tectonics. On Earth, the slow, grinding movement of continental plates acts as a planetary thermostat. It recycles carbon between the atmosphere and the mantle, preventing a catastrophic buildup of greenhouse gases or a global freeze. On HD 40307G, this same process could have been regulating the climate for eons, maintaining the stable conditions necessary for liquid water to persist on its surface. The combination of a stable star, an Earth-like orbit with seasons, and the planetary traits of a super-Earth paints a compelling picture of what this world could be like. Scientific models indicate that with an atmosphere similar to Earth's, its global average surface temperature could be remarkably temperate. It might be a world of dramatic and beautiful landscapes, with towering mountains pushed up by its strong tectonic forces and deep valleys carved by rainfall and rivers. Vast oceans could cover significant portions of its surface, with currents driven by winds and the planet's rotation, distributing heat from the equator to the poles and further moderating the climate. The presence of seasons would mean that these oceans could have rich nutrient cycles, with blooms of microscopic life potentially coloring the waters, while the land masses, if they exist, could see changing patterns of vegetation in response to the shifting sunlight. It is one of the few worlds we have found that seems to offer so many of the same comforting, stable conditions that allowed life to flourish on our own planet, making it a prime candidate in the ongoing search for a true Earth analog. But the journey to discover these distant worlds has been paved with historic milestones, and one of the most significant of all was the confirmation of a planet called Kepler 22b. Imagine the excitement in 2011 when the Kepler mission announced it had found its very first world orbiting squarely within the habitable zone of a sun-like star. This was not just another data point, it was a validation of the entire concept, a proof that the powerful method of watching for the tiny, periodic dimming of a star could indeed uncover planets where conditions might be just right for life. Located 600 light-years away in the constellation Cygnus, Kepler 22b orbits a star remarkably similar to our own Sun, a G-type main sequence star completing a full circuit every 290 days. That orbital period is just 25 days shorter than Earth's year, placing it in a strikingly familiar position within its system's habitable zone. The amount of stellar energy it receives is about 25% less than what Earth gets, a difference that a modest atmosphere could easily compensate for, making the potential for liquid water on this world a very real and thrilling possibility. The true enigma of Kepler 22b, however, lies in its size. With a radius about 2.4 times that of Earth, this planet sits squarely in the ambiguous middle ground between two very different kinds of worlds. It could be what astronomers call a super-Earth, a massive rocky planet with a solid surface. But with that much bulk, its surface gravity would be substantially stronger than ours, and it could have accumulated a truly staggering amount of water during its formation. In this scenario, Kepler 22b would not be an Earth analog with familiar continents and oceans, but a vast water world. Picture a global ocean, deep and uninterrupted, covering the entire planet from pole to pole. There would be no mountain peaks breaking the surface, no vast landmasses, just an endless, dark blue expanse. The pressures at the bottom of such an ocean would be immense, creating layers of exotic, hot ice that forms not from cold, but from incredible pressure, even in warm water. Life on such a world would be exclusively aquatic, potentially thriving around hydrothermal vents on the seafloor, completely isolated from the sun-drenched surface. The other compelling possibility is that Kepler 22b is not a water world at all, but a mini Neptune. This would mean it has a relatively small rocky core, but that core is enveloped by an immensely thick and deep atmosphere of hydrogen and helium, a gaseous envelope it captured during the early, chaotic days of the planetary system's formation. On such a planet, there is no solid surface to speak of, at least not one that we would recognize. As you descend through the atmosphere, the pressure and temperature would steadily increase. The hydrogen gas would gradually thicken into a supercritical fluid, and you would pass through layers of clouds made of water and ammonia before reaching a hot, slushy mantle of high-pressure ices. For habitability, this presents a much greater challenge. Any potential life would have to be a truly airborne organism, floating perpetually in the upper cloud decks, or it would need to endure the crushing, infernal conditions deep within the planet's fluid interior. The detection of water vapor in its atmosphere, which is a possibility for future telescopes, wouldn't necessarily point to surface oceans, but could simply be part of the complex chemistry of its extensive gaseous layers. What makes Kepler 22b so enduringly important, despite the uncertainty about its true nature, is its role as a trailblazer. It was the first of Kepler's many habitable zone discoveries, the world that truly opened the floodgates and showed us that such planets were not rare treasures but common features of our galaxy. It demonstrated that Sun-like stars could host worlds in the temperate zone, expanding the search beyond the red dwarfs that were initially thought to be the most likely hosts. Its discovery gave the entire field a massive confidence boost, proving that the technology and methods were working and that the hunt for a second Earth was a realistic, achievable scientific goal. Kepler 22b remains a celestial icon, a world that represents both a historic triumph and an ongoing mystery, a reminder that every answer we find in this great cosmic search also brings with it a new set of fascinating questions about the incredible diversity of planets that fill the universe. Now, let's turn our attention to a world that is practically a next-door neighbor in the vast expanse of our galaxy, a planet that serves as a powerful reminder of the delicate knife edge between a temperate paradise and a scorching hellscape. Just 14 light-years away, orbiting a quiet red dwarf star, we find Wolf 1061c. This super-Earth, with a mass about 4 times that of our own world, holds a unique and precarious position. It doesn't orbit in the comfortable center of its star's habitable zone. Instead, it circles much closer to the inner edge, skirting the boundary where things can quickly turn from warm to unbearably hot. This placement makes Wolf 1061c a fascinating natural laboratory, a real-world test case for one of the most critical questions in planetary science. What separates a life-giving world like Earth from a runaway greenhouse disaster like Venus? The key to understanding this world's dual nature lies in its atmosphere, or more precisely, the type of atmosphere it might possess. Imagine 2 possible futures for this same planet, dictated solely by the thickness and composition of its air. In one scenario, Wolf 1061c has an atmosphere similar to Earth's, a balanced mix of nitrogen, oxygen, and a modest amount of greenhouse gases like carbon dioxide. In this case, its position near the inner edge of the habitable zone could still allow for a stable climate. The amount of stellar energy it receives, while significant, might be manageable. With the right amount of reflective cloud cover and an active water cycle, the planet could efficiently regulate its temperature, potentially maintaining large bodies of liquid water on its surface. It could be a world of warm, shallow seas and humid tropical climates, a place where the conditions for life are challenging but far from impossible. But there is another, much more ominous possibility. If Wolf 1061c formed with or developed a much thicker atmosphere, rich in greenhouse gases like carbon dioxide or even sulfur compounds, its fate would be sealed. The intense stellar radiation bathing the planet, combined with that thick, heat-trapping blanket of air, could trigger a catastrophic positive feedback loop. Any initial warming would cause more water to evaporate from the oceans. Since water vapor is itself a potent greenhouse gas, this would trap even more heat, leading to further evaporation. This cycle would continue until the entire ocean boiled away into the atmosphere, leaving behind a barren, scorching world with a crushing atmospheric pressure and surface temperatures hot enough to melt lead. In this scenario, Wolf 1061c would not be a water world. It would be a twin of Venus, a permanent cautionary tale of how a planet can fall from grace. This dramatic divergence hinges on factors that scientists are eager to unravel. The planet's mass gives it a strong gravitational pull, which is excellent for holding onto an atmosphere, but that same mass also suggests a violent volcanic past. If the planet is geologically active, ongoing volcanism could be pumping enormous quantities of carbon dioxide into the air, constantly pushing the climate toward the runaway greenhouse threshold. Alternatively, if the planet has a functioning carbonate-silicate cycle similar to Earth's, where carbon dioxide is naturally pulled from the atmosphere and locked into rocks through weathering, it could have a built-in thermostat that has prevented such a catastrophe. The planet's tidal locking, which is likely given its close orbit, adds another layer of complexity. A thick atmosphere would be crucial for distributing heat from the permanent day side to the frozen night side. But if the atmosphere is too effective at trapping heat, the entire planet, including the night side, could overheat. The fine balance that determines Wolf 1061's true nature is a stark illustration of how habitability is not a permanent state, but a dynamic and fragile condition that must be actively maintained. The story of habitable worlds isn't always one of clear-cut discoveries. Sometimes it's a tale of scientific debate and a tantalizing, elusive prize. This brings us to one of the most controversial and captivating candidates in the entire exoplanet catalog, GJ581g. Located a mere 20 light-years away, this world was first announced in 2010, and its proposed characteristics were so compelling it sparked immediate and intense discussion within the astronomy community. The initial data suggested a planet with a mass just 3 to 4 times that of Earth, placing it firmly in the super-Earth category and strongly indicating a rocky composition. But the truly breathtaking part was its orbital position. If it exists, GJ581g would not be clinging to the inner or outer edge of its star's habitable zone. It would be orbiting right in the center, the sweetest spot of all. This placement would mean it receives a level of stellar energy from its red dwarf sun that could result in average surface temperatures remarkably similar to Earth's, creating a near-perfect environment for liquid water to exist without the need for an extreme greenhouse effect or a special atmospheric cocktail. For a brief, exciting moment, it seemed we had found an almost ideal Earth-sized world in an almost ideal location, practically in our cosmic backyard. The controversy surrounding this world is a fascinating lesson in the challenges of exoplanet detection. The planet was proposed based on years of painstaking radial velocity measurements of its host star, GJ581. This method doesn't see the planet directly. Instead, it detects the tiny wobble in the star's motion caused by the gravitational tug of an orbiting world. The signal for GJ581g was incredibly subtle, buried in the complex data of a system that was already known to host multiple other planets. Some research teams, reanalyzing the same data with different statistical techniques, found that the telltale wobble could be explained by a combination of stellar activity like sunspots and flares, and the gravitational interactions of the other confirmed planets in the system. They argued that what looked like a new world might just be noise in the data. The original discoverers, however, stood by their analysis, and subsequent studies have added new layers to the debate, with some supporting the planet's existence and others remaining skeptical. This scientific tug-of-war isn't a failure. It's how the process of discovery rigorously checks and rechecks itself, ensuring that every claim can withstand the toughest scrutiny. What makes this ongoing debate so consequential is the sheer potential of the world being debated. If GJ581g is real, it represents a kind of holy grail in the search for habitable planets. Its central location in the habitable zone of a quiet red dwarf star is a powerful combination. Unlike many other red dwarf planets that are likely tidally locked, some models suggested that GJ581g could be in a resonant orbit, spinning on its axis and experiencing a day-night cycle much like Earth. This would eliminate the extreme temperature differences between a permanent day-side and night-side, creating a far more uniform and stable global climate. With its Earth-like temperatures and potential for rotation, the planet could have weather patterns, ocean currents, and a geologically active surface that feels hauntingly familiar. Its substantial mass would give it a strong gravitational pull, ideal for holding onto a thick, protective atmosphere, and would likely power a magnetic field and active plate tectonics, all key ingredients for long-term planetary habitability. The possibility that such a world could exist just 20 light-years away is a staggering thought, a reminder that an almost perfect analog to our own planet might be orbiting one of the very closest stars to our solar system. The legacy of JJ581G, confirmed or not, is already profound. It pushed the limits of our detection methods and forced astronomers to develop more sophisticated tools to pull faint signals from the data. It highlighted the importance of stellar activity in muddying the waters of planet hunting and showed that the road to discovery is often paved with healthy, rigorous disagreement. Most importantly, it solidified in the public imagination the very real possibility of a nearby habitable world. Whether JJ581G is ultimately verified by future telescopes or fades into history as a beautiful, unconfirmed possibility, it serves as a powerful symbol of the drive to find another Earth. It represents the hope that drives astronomers to peer ever deeper into the data, searching for that faint, rhythmic wobble that could reveal a new home among the stars. Now, let's consider a world that perfectly illustrates the critical role of planetary mass in the search for habitability. 37 light-years from Earth, orbiting a K-type star in the constellation Vela, we find the super-Earth HG85512b. This planet, with a mass at least 3.6 times that of our own world, presents a fascinating climatic puzzle. Its orbital period of just 58 Earth days places it extremely close to its host star, and on paper, the amount of stellar energy it receives is actually slightly more than what Venus gets from our Sun. At first glance, that statistic might sound like a death sentence, immediately bringing to mind the hellish 460 degrees Celsius surface of our sister planet. But mass changes everything. A planet's ability to create and, more importantly, retain a substantial atmosphere is a direct function of its gravitational pull, and HD85512b has the heft to potentially hold onto a very different kind of air than the scorching, carbon dioxide-dominated hellscape of Venus. The potential for habitability here hinges entirely on the composition and reflectivity of its atmosphere. Imagine two different blankets wrapped around this world. The first scenario is the Venus-like path. If its atmosphere is thick with carbon dioxide and has minimal cloud cover, the resulting runaway greenhouse effect would indeed bake the surface, making liquid water impossible. But there is another, more promising possibility. What if HD85512b has an atmosphere with a significant amount of cloud coverage? High, bright clouds, like the wispy cirrus clouds we see on Earth, are incredibly effective at reflecting sunlight back into space. If this planet's air is filled with such reflective particles, those clouds could act like a planetary sunshade, bouncing a large portion of the incoming stellar energy away before it ever has a chance to heat the surface. This would dramatically lower the overall temperature, potentially bringing it down into a range where water could exist as a liquid. It's a delicate balancing act where the atmosphere must be thick enough to provide sufficient greenhouse warming to prevent global freezing, yet its upper layers must be reflective enough to offset the intense stellar flux from its close orbit. This concept of planetary albedo, or reflectivity, is a powerful climate regulator that we often overlook. Our own Earth maintains its comfortable temperature through a combination of greenhouse gases and a certain level of reflectivity from ice, snow, and clouds. For HD85512b, this balance is even more critical. Scientific climate models specifically developed for this planet have shown that if its atmosphere has an Earth-like composition and a cloud cover of at least 50%, its surface temperatures could easily be maintained well within the range needed for liquid water. This isn't just speculation, it's a quantitative demonstration of how a world that receives Venus levels of solar radiation could, under the right atmospheric conditions, become a temperate oasis. The presence of such extensive cloud cover would also suggest an active hydrological cycle, with water evaporating, forming clouds, and precipitating back to the surface, all of which are key processes for a living world. The star it orbits adds another layer of favorable conditions. HD 85512 is a K-type star, older and more stable than many of the flaring red dwarfs we've encountered. Its calm nature means the planet hasn't been subjected to billions of years of atmosphere-stripping stellar tantrums, giving it a far better chance to hold onto the very air that defines its climate fate. The planet's substantial mass further supports this, as its strong gravity makes atmospheric loss to space a very slow process. When you combine its mass-derived atmospheric stability, the potential for a reflective cloud deck, and its orbit within the broader habitable zone, HD 85512b emerges as a compelling case study. It teaches us that the habitable zone is not a rigid line, but a fluid concept that depends as much on a planet's atmospheric personality as it does on its distance from its star. This world challenges the simple Venus analogy and expands our understanding of where we might find environments capable of nurturing life. But as we push farther out into the galaxy, we encounter worlds that challenge our very definitions of what a rocky planet can be. Venturing an immense 2,500 light-years from Earth, we find Kepler 443b, a testament to the sheer diversity of planetary forms. This world is a giant compared to our own, with a radius about 2.3 times that of Earth. For a long time, astronomers might have assumed a planet of this scale would almost certainly be a mini Neptune, a gaseous world with no solid surface. But Kepler 443b defies that simple categorization. Detailed analysis of its characteristics suggests something remarkable. There is roughly a 50% probability that this immense world is in fact a rocky super-Earth. This statistical coin toss at such a vast distance is a profound revelation. It tells us that the dividing line between a massive rocky planet and a small gas giant is far blurrier than we once thought, and that the potential for solid, potentially life-friendly surfaces might exist on worlds of a scale we previously considered uninhabitable. The concept of a rocky planet this large is both fascinating and daunting. Imagine a world with more than twice the surface area of Earth, all composed of continental rock and metal. The landscapes would be epic in proportion, with mountain ranges that could dwarf the Himalayas and vast, rolling plains stretching to horizons that seem infinitely far away. The gravitational pull on such a world would be substantially stronger than what we experience. A person who weighs 150 pounds on Earth would feel like they weigh nearly 350 pounds on the surface of Kepler 443b. This intense gravity would dramatically shape the environment. The atmosphere would be much denser and pressed closer to the ground, potentially creating a thick, hazy sky. Erosion would work differently, likely wearing down mountains faster and creating lower, more rounded topography over time. Even the very chemistry of the planet could be affected, with volcanic eruptions behaving differently under such immense pressure, potentially creating bizarre, slow-moving flows of super-dense lava. The prospect of a solid surface on a world this massive expands the canvas of possibility, suggesting that habitable environments might not be limited to Earth-sized spheres, but could exist on these planetary titans. Of course, the existence of a solid surface is just one piece of the habitability puzzle. Kepler 443b orbits within the habitable zone of its K-type host star, a star slightly cooler and smaller than our Sun. This means it receives the right amount of stellar energy to, in theory, support liquid water. However, that 50% probability of being rocky also carries with it a 50% chance that it is a gaseous mini-Neptune. This fundamental uncertainty is the central mystery of this distant world. If it is a mini-Neptune, any water present would likely be in the form of superheated steam or exotic, high-pressure ices deep within its gaseous envelope, with no defined surface for life as we know it to gain a foothold. But if it is rocky, its massive size becomes a double-edged sword. The strong gravity that gives it a solid surface would also make it exceptionally good at holding onto a crushing atmosphere. The surface pressure could be dozens or even hundreds of times greater than on Earth, creating a greenhouse effect so powerful that it could potentially overcook the planet, turning what should be a temperate zone into a scorching pressure cooker more akin to Venus than to Earth. This delicate balance is what makes the study of such distant super-Earth so critical. Kepler 443b serves as a powerful example of how a planet's potential for life is not determined by a single factor, but by a complex and finely tuned interplay of many variables. Its location in the habitable zone is a necessary starting point, but its ultimate nature depends on its formation history, its bulk composition, and the subsequent evolution of its atmosphere. The ongoing quest to resolve this uncertainty is driving the development of next-generation space telescopes. By analyzing the starlight that filters through the planet's atmosphere during a transit, astronomers hope to detect the chemical signatures that would reveal its true identity. A detection of hydrogen and helium would point toward a gaseous world, while signs of heavier molecules like carbon dioxide or water vapor in a thinner atmosphere would bolster the case for a rocky behemoth. Kepler 443b, a faint speck of light from a distant star, thus embodies the next great challenge in exoplanet science, not just finding worlds in the right place, but piercing the veil of their physical nature to understand which of them are truly worlds like our own and which are something else entirely. And now, let's turn our gaze to a star that has featured in science fiction for generations as a potential home for other civilizations. A star that is, in many ways, a near twin to our own Sun. Just 12 light-years away, a distance that places it among our very closest stellar neighbors, shines Tau Ceti. This star is a G-type main sequence star, just like our Sun, though it's slightly smaller and less luminous. For astronomers searching for habitable worlds around Sun-like stars, Tau Ceti is a primary target, a beacon of familiarity in the vastness of space. And within its system, we find a world of profound possibility and equally profound uncertainty, Tau Ceti e. This super-Earth, with a mass at least 4 times that of our own planet, occupies a position that makes it one of the most intriguing and pivotal case studies in the entire hunt for life. It doesn't orbit in the comfortable center of the habitable zone. Instead, it circles perilously close to the inner edge, a location that places its entire future in the hands of its atmosphere. The story of Tau Ceti e is a tale of 2 planets, a world balanced on a climatic knife edge where the nature of its air could mean the difference between a hellish wasteland and a temperate oasis. The fate of this world hinges entirely on a delicate atmospheric balancing act. On one hand, its position means it receives a significant amount of stellar energy from its Sun-like star. If Tau Ceti e has a thick atmosphere dominated by greenhouse gases like carbon dioxide, this proximity to its Sun would trigger a catastrophic runaway greenhouse effect. In this scenario, the intense stellar heat would cause any oceans to boil, releasing vast quantities of water vapor, itself a potent greenhouse gas, into the atmosphere. This would trap even more heat, leading to a positive feedback loop from which there is no return. The entire ocean would eventually be lost to space, and the surface would become a scorching, high-pressure inferno, much like Venus in our own solar system. Tau Ceti e would become a super-Venus, a stark reminder of how easily a world can fall from a potentially life-giving state into a permanent furnace. Yet there is another, far more hopeful possibility. What if Tau Ceti e has a more moderate, Earth-like atmosphere? In this scenario, the presence of reflective cloud cover could be its saving grace. High, bright clouds could act as a planetary sunshade, bouncing a substantial portion of the incoming stellar radiation back into space before it can heat the surface. Furthermore, if the planet has an active carbon cycle similar to Earth's, where plate tectonics pull carbon dioxide out of the atmosphere and lock it away in rocks. It could possess a built-in thermostat that prevents a greenhouse catastrophe. With these regulatory mechanisms in place, the amount of energy Tau Ceti receives could result in a surprisingly temperate climate. It could be a world with warm, shallow seas and a thick, protective atmosphere, where the conditions at the surface are not only habitable, but could be genuinely comfortable for life as we know it. This dramatic divergence is what makes the planet such a compelling target for study. It represents a real-world test of our theories about planetary climate and the fine line that separates a living world from a dead one. The scientific intrigue surrounding Tau Ceti is amplified by its host star's unique characteristic. Unlike many other systems we've explored, the Tau Ceti system is known to contain a massive disk of dust and debris, far more substantial than the debris disk in our own solar system. This suggests a dynamic and possibly violent environment, with a much higher frequency of comet and asteroid impacts than Earth experiences. For a young planet, such a bombardier environment could have delivered the water and organic molecules that are the essential building blocks of life. However, for an established biosphere, a high impact rate could pose an existential threat, potentially causing mass extinctions that reset the evolutionary clock. This adds another layer of complexity to the potential history of Tau Ceti. Did it gain a rich supply of life's ingredients from this cosmic delivery system, or has it been repeatedly sterilized by catastrophic collisions? The answer could determine whether its surface is a pristine laboratory for prebiotic chemistry or a world that has repeatedly struggled to allow life to gain a foothold. This very question is what drives the ongoing, cutting-edge searches for biosignatures in the light we receive from this system. While directly imaging Tau Ceti is currently beyond our reach, astronomers are using the most advanced spectroscopic techniques to analyze the combined light of the star and its planets. The goal is to detect the faint chemical fingerprints of gases in the planet's atmosphere as it transits, or to pick out its specific light from the glare of its star. The hunt is on for molecules like oxygen, methane, and ozone gases that, in certain combinations, are strong indicators of biological activity because they are quickly destroyed by natural processes unless they are continuously replenished. Finding such a signature in the atmosphere of a planet perched on the inner edge of the habitable zone would be revolutionary. It would tell us that some worlds can not only survive in this precarious position, but can indeed thrive, developing and sustaining a biosphere that actively manages its own climate. Tau Ceti, a world of two potential destinies, thus stands as a powerful symbol of our quest. It challenges us to refine our models and sharpen our observational tools, pushing us to answer one of the most fundamental questions we can ask about a distant world. Is it a warning or is it a promise? Our journey through the cosmic neighborhood now brings us to a world that perfectly embodies the high-stakes nature of this search. A planet where the difference between a tropical paradise and a scorching hellscape could come down to the composition of its air. Just 16 light-years away, a distance that is almost laughably small on the galactic scale, orbits Gliese 832c. This super-Earth, with a mass at least 5 times that of our own world, presents astronomers with one of the most compelling and cautionary tales in the catalogue of potentially habitable planets. The initial data was incredibly promising, even earning it a high ranking on the Earth Similarity Index. It orbits its calm red dwarf star in just 36 days, and because that star is so much cooler than our Sun, this incredibly short year still places the planet squarely within the habitable zone. In fact, the calculations show it receives roughly the same amount of stellar energy from its Sun as Earth does from ours. On paper, that sounds like a recipe for a perfect Earth twin. But that's where the simplicity ends and the fascinating complexity begins. The central puzzle of Gliese 832c lies in its substantial mass. A planet that is 5 times heavier than Earth has a much stronger gravitational pull, and this force has profound implications for its atmosphere. During the planet's formation, this strong gravity would have allowed it to pull in and hold onto vast quantities of volatile gases, potentially building up an atmosphere far thicker than our own. This is where the planet's story splits into two dramatically different possibilities, a fork in the cosmic road leading to entirely different destinies. In one scenario, that thick atmosphere is a blessing. It could provide robust shielding from cosmic rays and stellar radiation, and with the right mix of gases, it could effectively distribute the star's heat around the globe, creating a stable, warm climate with liquid water oceans on its surface. It could be a world of dramatic weather and deep blue seas, a super Earth where the conditions for life are not just possible, but perhaps even more stable than on our own planet. But there is a second, more ominous path this world could have taken, a path that serves as a sobering reminder of the delicate balance required for habitability. If the atmosphere of Gliese 832c is too thick and dominated by greenhouse gases like carbon dioxide, the situation flips from promising to perilous. The same stellar energy that gives Earth its temperate climate could, on this world, get trapped by that oppressive atmospheric blanket. This would trigger a runaway greenhouse effect. The initial warming would cause water to evaporate from the oceans. Since water vapor is itself a powerful greenhouse gas, this would trap even more heat, leading to even more evaporation. This vicious cycle would continue unchecked until the entire ocean boiled away into the atmosphere, leaving behind a barren, scorching landscape under a crushing, toxic sky. In this scenario, Gliese 832c would not be an Earth twin at all, but a super-sized Venus, a stark monument to how easily a world with the right amount of starlight can become an uninhabitable furnace. This planetary duality makes Gliese 832c a critical case study for astronomers. It sits right on that theoretical knife edge, and determining its true nature is essential for refining our models of planetary evolution. The key to unlocking its mystery lies in analyzing the chemical composition of its atmosphere, a task that falls to powerful telescopes like the James Webb Space Telescope. By observing the starlight that filters through the planet's air as it passes in front of its star, scientists can search for the telltale signatures of different gases. Finding evidence of a hydrogen-dominated atmosphere would point toward a mini Neptune, a world without a solid surface. Detecting signs of a thinner, Earth-like atmosphere with water vapor and nitrogen would be a thrilling indication of a potentially habitable super-Earth. But if the data reveals the thick, carbon dioxide-rich haze of a runaway greenhouse, it will be a profound lesson. It would teach us that receiving Earth-like levels of stellar energy is not enough. A planet must also have the right size, the right geology, and the right atmospheric history to walk the narrow path toward life. Gliese 832c, a nearby world of immense promise and equally immense risk, therefore stands as a cosmic question mark, challenging us to look closer and understand the subtle forces that separate a living world from a dead one. Venturing much deeper into the galaxy, we find a world that highlights the incredible power of climate modeling to transform a single day to point into a vivid potential paradise. 1,500 light-years from Earth, in the constellation Lyra, orbits Kepler 283c, a super-Earth that serves as a brilliant example of how scientists can take the fundamental metrics of a planet, its size, orbit, and star, and paint a compelling picture of its possible environment. This planet, with a radius about 1.8 times that of our own world, circles a star noticeably cooler and smaller than our Sun. Its orbit is tight, with a year that flashes by in just 93 Earth days, but this proximity is precisely what places it securely within the star's habitable zone. The raw data is promising, but it is the sophisticated computer simulations that breathe life into this distant speck of light, revealing a climate scenario so inviting it feels almost like a blueprint for a second Earth. These models, which incorporate the complex physics of atmospheric circulation, heat retention, and stellar radiation, indicate that if Kepler 283c possesses an atmosphere with a composition and pressure similar to our own, its global average surface temperature could be remarkably temperate, resting comfortably between 0 and 40 degrees Celsius. That is a stunningly narrow and perfect range, one that spans from the freezing point of water to a warm summer's day, entirely encompassing the conditions needed for liquid water to pool, flow, and persist across the planet's surface. The implications of this specific temperature window are profound. It means that without needing any extraordinary atmospheric concoctions or a bizarre geological setup, this world could naturally achieve a stable, water-friendly climate. On a planet with these conditions, you wouldn't find one hemisphere scorching under unbearable heat while the other is locked in a permanent ice age. Instead, the climate could be broadly temperate, with vast oceans moderating the temperature and weather patterns distributing heat from the equator toward the poles. Imagine standing on a coastline of Kepler 283c, looking out at an ocean that behaves much like our own Atlantic or Pacific, with waves lapping at shores that could be rocky cliffs or sandy beaches. The air could feel familiar, with a pressure that allows water to remain liquid without instantly boiling away or freezing solid. This is the kind of environment where the chemical reactions that lead to life can proceed at a leisurely pace, where probiotic molecules can mix and interact in shallow tidal pools or deep ocean basins for millennia. The planet's size adds to this promising picture. As a super-Earth, it has enough gravity to hold onto a substantial atmosphere, protecting its surface from cosmic radiation and creating the pressure needed to keep water in its liquid state. Its larger surface area also suggests a world of immense geographic diversity, with the potential for sprawling continents and deep ocean trenches, offering a wide variety of niches where life could initially take hold and then evolve in countless different directions. However, this idyllic vision rests on one monumental if, the assumption of an Earth-like atmosphere. The climate models provide a breathtaking glimpse of what could be, but they cannot tell us what is. The atmosphere is the wild card, the great unknown that defines the current mystery of Kepler 283c. A planet's air is its personality, the factor that dictates whether it will be a lush, living world or a barren rock. Kepler 283c could have followed a number of different paths since its formation billions of years ago. It might have developed an atmosphere thick with nitrogen and oxygen, just like Earth, creating the very conditions the models predict. Alternatively, volcanic activity over eons could have filled its air with a dense shroud of carbon dioxide, triggering a runaway greenhouse effect that evaporated its oceans and left it a scorching wasteland similar to Venus. Another possibility is that intense radiation from its star in its early, more volatile years could have stripped the planet's atmosphere away entirely, leaving it an airless, desolate landscape pockmarked by craters, much like Mercury. The difference between a temperate oasis and a sterile hell is literally a matter of a few molecules of gas per cubic centimeter. This is the central question that drives the scientific pursuit of this distant world, a question that can only be answered by peering directly at the planet's atmospheric composition. This is where the next generation of astronomy comes into play, turning Kepler 283c from a theoretical candidate into a tangible target for exploration. The method used to study its atmosphere is as elegant as it is powerful. When the planet passes directly in front of its host star from our perspective, a tiny fraction of the star's light filters through the planet's thin, glowing limit's atmosphere. By analyzing this filtered starlight with immensely sensitive instruments like those on the James Webb Space Telescope, astronomers can break it down into a spectrum, a unique chemical fingerprint. Each type of gas in the atmosphere leaves a specific dark line in this spectrum, absorbing light at characteristic wavelengths. The hunt is for the telltale signs of water vapor, carbon dioxide, methane, and ozone. Detecting a combination of these gases, particularly water vapor alongside oxygen and methane, would be a monumental discovery. It wouldn't just confirm the potential for liquid water, it would point toward an atmosphere that is not in a state of simple chemical equilibrium, an atmosphere that is being actively managed and altered, possibly by the presence of life itself. Kepler 283c, therefore, represents a critical stepping stone. It is a world where the theoretical groundwork has been laid, where the models provide a clear and optimistic hypothesis. The next step is to test that hypothesis, to move from a beautiful simulation on a supercomputer to the hard, empirical data that will tell us whether this distant world is truly the welcoming, water-rich haven it appears to be. While we've marveled at super-Earths and water worlds, the ultimate prize in this cosmic search is a world that mirrors our own in almost every way, a true second Earth. And that brings us to a candidate that, on paper, comes closer than almost any other. Meet KOI 3010.01, a world whose very profile reads like a description of our own planet, but written in the language of distant starlight. This candidate, discovered in the vast data archive of the Kepler mission, earns its reputation from a scientific metric known as the Earth Similarity Index. This index compares a planet's key properties, its size, density, surface temperature, and escape velocity to Earth's, with a perfect match scoring 1.0. KOI 3010.01 achieves a remarkably high score, placing it among the top contenders for the most Earth-like world we have ever identified. This isn't just a rough approximation, it's a mathematical assessment that suggests a profound level of similarity. A world built to a blueprint we know can support a rich and complex biosphere. The foundation of this similarity lies in its host star. Unlike the faint red dwarfs that dominate our list of habitable candidates, KOI 3010.01 orbits a star that is a close cousin to our own Sun. This G-type star provides a familiar kind of sunlight, a stable and consistent flow of energy that has allowed life on Earth to thrive for billions of years. Orbiting within this star's habitable zone, the planet receives an amount of stellar energy almost identical to what Earth receives. This means that the fundamental driver of climate and weather, the energy from its sun, is virtually the same. From the surface of this world, the sun in the sky would look very much like our own, casting similar shadows and providing the same quality of light that drives photosynthesis on our planet. This stellar context is a crucial advantage. A sun-like star offers a far more stable and predictable environment than the turbulent red dwarfs, with a much lower risk of atmosphere-stripping flares, giving any potential life a peaceful and enduring stage upon which to evolve. But the parallels run even deeper. The estimates for KOI 3010.01 size and mass point toward a rocky world with a surface gravity very close to our own. This is a critical distinction from the many super-Earths we've encountered. You wouldn't feel crushingly heavy walking on this world. The experience of weight, the flow of rivers, and the very physics of its geology would feel hauntingly familiar. Its calculated density strongly suggests a composition of rock and metal, much like Earth, meaning it almost certainly has a solid surface with continents, mountain ranges, and vast basins that could hold liquid water. The estimated equilibrium temperature, when combined with the potential for an Earth-like atmosphere, points to global average conditions that could easily support liquid water oceans. Imagine a world with a climate zone distribution similar to our own icy polar caps, temperate mid-latitudes, and a warm tropical belt around the equator. It's a picture of a world not of extreme or alien environments, but of comfortable, Earth-like normality, a planet that seems to have followed the same recipe for habitability that our own world did. Of course, the single greatest mystery surrounding KOI 3010.01, and the reason it remains a candidate rather than a confirmed planet, is the nature of its atmosphere. The Earth Similarity Index gives us a powerful statistical argument, but it cannot tell us what the air is actually made of. This is the great frontier in exoplanet science, and this world sits right at its center. The planet's potential is entirely shaped by the blanket of gases that envelops it. If it has developed an atmosphere with a balance of nitrogen, oxygen, and trace greenhouse gases similar to Earth's, then the models suggest it could be a lush, living world, a virtual twin of our own planet. However, if its atmospheric history took a different path, the story could be completely different. A thicker, carbon dioxide-dominated atmosphere could have triggered a runaway greenhouse effect, turning it into a scorching hellscape like Venus. Alternatively, if it lost its atmosphere early in its history due to a more active young star, it could be a cold, barren desert like Mars. The difference between a second Earth and a sterile rock is literally a matter of a few key gases, a delicate balance that we are only now learning to detect across the light years. This is what makes KOI 3010.01 such a high-priority target for the future. While its initial detection was made by the Kepler telescope, confirming its existence and studying its atmosphere will require the power of next-generation observatories like the James Webb Space Telescope and future extremely large ground-based telescopes. The goal will be to catch the planet as it transits in front of its star and analyze the starlight that filters through its atmospheric limb. Scientists will be searching for the chemical fingerprints of water vapor, which would confirm the presence of the key ingredient for life. Beyond that, they will hunt for the telltale biosignatures, gases like oxygen and methane that, when found together, are difficult to explain through geology alone and strongly suggest the presence of biology. Finding such a combination in the atmosphere of a world as Earth-like as KOI 3010.01 would arguably be one of the most significant discoveries in the history of science. It would transform this candidate from a promising set of numbers into a living, breathing world, a place that doesn't just resemble Earth, but one that may actually share its most profound quality, the spark of life. Yet another reminder of the delicate balance required for life comes from a world that, on the surface, seemed to have everything going for it. Meet Kepler 438b, an Earth-sized planet discovered in the Kepler data, located about 470 light-years away. In terms of its basic physical properties, this world was a standout candidate. Its radius is just 12% larger than Earth's, making it one of the most Earth-like planets we've ever found in size. It orbits comfortably within the habitable zone of its red dwarf star, and the amount of stellar energy it receives is about 40% more than what Earth gets from our Sun. That extra energy, while significant, is not a deal-breaker. With a reflective atmosphere and active cloud cover, such a world could still easily maintain temperate surface conditions and vast liquid water oceans. For a time, Kepler 438b was celebrated as one of the most promising analogues to our own planet, a world that checked the critical boxes for size and orbital position. However, the true story of this world's potential is not written in its orbit or size, but in the violent nature of the star it calls home. The host star, Kepler 438, is a red dwarf, but it belongs to a particularly volatile class. Observations have revealed that this star is a proverbial cosmic tempest, subject to frequent and devastating superflares. These aren't just slightly larger versions of solar flares, they are cataclysmic events, orders of magnitude more powerful than anything our Sun has produced in recorded history. A single one of these superflares can unleash as much energy in a few hours as our Sun does over hundreds of thousands of years. For a planet like Kepler 438b, which orbits very close to its star to stay within the habitable zone, these events are not occasional inconveniences, they are existential threats. The primary danger of these flares isn't the flash of light or the immediate heat. It's the torrent of high-energy X-rays and ultraviolet radiation that accompanies them, coupled with colossal eruptions of charged particles known as coronal mass ejections. When such a flare erupts, it bathes the nearby planet in a sterilizing bath of radiation. This radiation doesn't just scorch the surface, it attacks the very foundation of a stable climate, the atmosphere. The high-energy photons and particles have enough force to knock atmospheric molecules right out into space, a process known as atmospheric erosion. Think of it as a planetary sandblaster, relentlessly scouring away the protective blanket of air molecule by molecule over millions of years. If Kepler 438b ever did have a thick, Earth-like atmosphere in its distant past, the relentless barrage from its star has likely stripped it away, leaving the planet a barren, airless rock, exposed directly to the harsh vacuum of space and the full fury of every subsequent stellar outburst. This presents a heartbreakingly stark contrast. On one hand, we have a world with an Earth-like size and an orbit that suggests perfect conditions for liquid water. On the other, we have a stellar environment so hostile that it actively destroys the very conditions it creates. The case of Kepler 438b powerfully demonstrates that simply being in the habitable zone is not enough. A planet's star is not just a source of light and heat. It is the dominant force that shapes the planet's entire long-term environment. A quiet, stable star can nurture a world for billions of years, while a tempestuous one can render a perfectly positioned planet completely uninhabitable. The tragedy of Kepler 438b is that it had all the right ingredients for life except for one, a calm parent star. It stands as a sobering lesson in our search, reminding us that we must look beyond the planet itself to the character of the star it orbits, understanding that stellar activity is every bit as crucial as orbital distance when judging a world's true potential for life. And so we arrive at our final world, a planet that challenges our most fundamental assumptions about where life can exist and what a habitable planet even looks like. Welcome to GJ1214b, a super-Earth that orbits a red dwarf star just 48 light-years away in the constellation Ophiuchus. At first glance, this world seems to defy all the rules we've discussed. It is not comfortably situated in the middle of its star's habitable zone. In fact, it circles its sun in a blisteringly fast orbit of just 1.6 Earth days, so close that its surface temperature without an atmosphere would be scorchingly hot. Yet, it is this very proximity and the unique physical characteristics it creates that make GJ1214b one of the most intriguing and paradigm-shifting worlds on our list. It forces us to expand our imagination beyond Earth-like surfaces and consider that the most common abodes for life in the cosmos might not be terrestrial landscapes at all, but vast, dark, global oceans beneath an alien sky. The defining mystery of GJ1214b and the key to its potential is what astronomers discovered when they first tried to peer into its atmosphere. This planet was one of the first super-Earths whose atmosphere we were able to directly study, and the results were startlingly uniform. No matter when or how we looked at it, the planet's atmosphere appeared almost completely featureless across a wide range of wavelengths. It was a flat, blank slate, lacking the strong chemical fingerprints of common gases like hydrogen, water vapor, or methane that we might expect to see. For scientists, this blandness was actually a profound clue. It pointed strongly toward an atmosphere that is not thin and clear like Earth's, but one that is incredibly thick and hazy, likely blanketed by high-altitude clouds or a deep layer of photochemical haze. This isn't a wispy veil of air, it is a massive, opaque shroud, a global blanket that completely envelops the planet and hides its surface from our view. This thick atmosphere is almost certainly the planet's primary defense mechanism, a shield that has allowed it to manage the intense stellar energy from its close orbit and potentially create a stable, if utterly alien, environment below. This discovery led scientists to propose a breathtaking model for what GJ1214b might actually be, a water world of almost unimaginable scale. The prevailing theory suggests that this planet is not a rocky super-Earth like many others, but rather a mini Neptune with a truly oceanic nature. Its composition is thought to be a relatively small core of rock and metal, making up only a fraction of its total mass, while the vast majority of the planet is composed of water in various forms. But this is not a world with distinct oceans and continents. Instead, picture a single, uninterrupted global ocean, but one that is not hundreds of meters deep like Earth's. This ocean could be hundreds of kilometers deep. The sheer volume of water on this single planet could dwarf all the water in Earth's oceans combined by orders of magnitude. As you descend from the top of the thick, steamy atmosphere, you would eventually reach an ocean surface. But this surface would not be a sharp boundary like on Earth. It would be a gradual transition into a fluid realm where the conditions are unlike anything we know. The environment within this abyssal ocean would be defined by one overriding force: immense pressure. At the very top, near what we might call the surface, the pressure would already be dozens of times greater than the deepest part of Earth's Mariana Trench. As you journey downward through the perpetual darkness, the pressure would climb to thousands, and then even hundreds of thousands of times Earth's atmospheric pressure. Under these staggering conditions, the physics of water itself begins to change. Long before you reach the rocky seafloor, the pressure would become so extreme that the water molecules would be forced into exotic, hot forms of ice. Not ice formed from cold, but ice formed from pressure alone, crystals with names like Ice 6 and Ice 7 that are denser than liquid water and remain solid even at temperatures far above boiling. This means the interior of GJ1214b could be a layered structure like a cosmic onion, a thick, steamy atmosphere, a global liquid water ocean hundreds of kilometers deep, and beneath that, a mantle of hot, high-pressure ice, all surrounding a small, rocky core. For life to exist in such a place, it would have to be fundamentally different from the surface-based, sun-dependent life we are familiar with. The thick cloud layer would block virtually all sunlight from ever reaching the ocean, creating a world of permanent and absolute darkness. There would be no day-night cycle, no seasons, and no energy from photosynthesis. This seems like a bleak prospect until we look at our own planet and find a perfect analogy in the deep-sea hydrothermal vents. At the bottom of Earth's oceans, far from the sun's reach, entire ecosystems thrive in total darkness. They are powered not by light, but by chemical energy, specifically by the minerals and heat spewing from volcanic vents on the ocean floor. On GJ1214b, this same process could be happening on a planetary scale. The planet's rocky core, heated by the decay of radioactive elements and the residual energy of formation, would be geologically active. The seafloor, at the boundary between the rock and the deep ocean or ice mantle, would be dotted with countless hydrothermal vent systems. These vents would act as natural reactors, providing a constant flow of energy-rich chemicals and warmth into the surrounding darkness. In this context, the global ocean of GJ1214b is not a barren wasteland, but a potential incubator. The sheer volume of water provides a stable medium, and the vents provide the energy and chemical building blocks. Life here would be completely isolated from the violent stellar environment above, protected by thousands of kilometers of water and ice. It could have originated and evolved over billions of years in a dark, pressurized world, utterly unaware of the star it orbits or the universe beyond its watery shell. The organisms that might call this place home could be truly alien, adapted to crushing pressures, constant warmth, and a metabolism based entirely on chemosynthesis. They might float in the deep currents or cluster around the volcanic vents on the seafloor, forming complex food webs in the eternal night. GJ1214b, therefore, stands as the ultimate testament to the versatility of life. It teaches us that a planet doesn't need a solid surface, a sun-like star, or even sunlight to be habitable. It simply needs a stable liquid medium, a source of energy, and the right chemistry. This distant water world expands the canvas of possibility. suggesting that the most common homes for life in our galaxy might not be the familiar rocky planets like Earth, but the dark, deep, and endless oceans of hidden water worlds. From our closest stellar neighbors to distant worlds thousands of light years away, these 25 planets represent far more than just a list of intriguing names. They are signposts in a fundamental revolution in our understanding of the cosmos. Each one, from the tempest-tossed Proxima Centauri b to the deep, dark ocean of GJ 1214b, tells us that the basic ingredients for life, rocky surfaces, liquid water, stable energy sources, are not rare treasures but common features scattered throughout the Milky Way. We are moving from an era of wondering if other Earths exist to an era of cataloging the stunning diversity of forms they can take. This is the profound shift these worlds represent. Habitability is not a single, narrow set of conditions, but a spectrum of possibilities, a palette of environments where the chemistry of life could find a way. The universe is not a sterile void, it is a canvas of potential, and on that canvas we have now identified 25 brilliant points of light where the story of life may have already begun or may yet be written. This incredible journey of discovery is accelerating at a breathtaking pace, fueled by a new generation of tools that are fundamentally changing what we can see and understand. The James Webb Space Telescope is already peering into the atmospheres of these distant worlds, searching for the chemical fingerprints of water vapor, methane, and oxygen. But this is only the beginning. Planned observatories like the Habitable Worlds Observatory and the extremely large telescopes being built on mountaintops in Chile will possess capabilities that seem like science fiction today. They will not just detect atmospheres, they will map them, studying how weather patterns shift across the days and years of an alien planet. They will hunt for the subtle, combined signatures of gases that are difficult to explain without biology, the biosignatures that would signal we are not alone. The 25 worlds we've explored today are the prime targets, the subjects of intense scrutiny that will move from being points of light to being worlds with known climates, weather, and perhaps even surface features. The data we are about to collect will transform these candidates from fascinating possibilities into characterized worlds, each with its own unique story of formation, evolution, and potential. Ultimately, this search for habitable worlds is a search for context, for a deeper understanding of our own place in the vast cosmic ocean. For all of human history, Earth was a solitary haven, a singular oasis of life in what appeared to be an empty and silent universe. These 25 planets and the thousands more like them waiting to be found shatter that ancient perspective. They teach us that our planet is not a lonely accident, but one of countless experiments in planet building and potentially in life itself. Every one of these worlds is a question posed to the universe. What happens when the same cosmic processes that shaped our world are set in motion around another star? The answers are proving to be more varied and wondrous than we ever imagined. This is not the end of the journey, it is the very beginning of a new chapter in human exploration. We are no longer just gazing at the stars, we are learning to read their planetary systems, and in doing so, we are taking the first steps toward truly understanding our cosmic neighborhood.